Alright, good morning learners. Today I will be teaching you about basic set theory. When we talk about basic set theory, it is the basics as, for example, empty sets, set memberships, or even the large union and intersection symbols. So we are going to learn these, but before we even get into set theory, I want you guys to really take note of this real quick. So let me try to find it on my reference papers. It's basically my notes. The first thing that you should know is we're gonna have some blackboard bold symbols like this Z over here. I think that looks a bit too bad there. It looks a bit better now. This denotes the set of all integers. So it's basically just a set of the whole numbers, like -2, -1, 0, 1, 2, and so on, you know? So that's what we mean by integers. Now I'm gonna write it here. You may notice my handwriting might be a bit bad. Yeah, let me just fix that real quick. Okay, I fixed it. So it's just gonna be -1, 0, 1, 2, 3, and etc. Keep in mind that the negative numbers can also start from somewhere else. Now let's see Q rational numbers. So rational numbers are basically numbers that you can just express as a fraction, like P over Q. Oh, for example, 1 over 2, 2 over 5, you know, etc., etc. And if it's an irrational number, it would be something like pi, Euler's constant, Euler's number. Sorry, this is Euler's constant and this is Euler's number, to clear up any confusion. Now let's go look at the natural numbers. We write it like this. It's a nice bold N, and in my opinion it looks pretty cool. So natural numbers start from 0, 1, 2, 3, and so on. They don't have negative numbers because they're positive whole numbers. Now, the last thing you need to know for your, I guess you could call it number theory, is real numbers. That just means the combination of everything that we mentioned earlier. If it's not a real number, like I is a complex number, it's not a real number. You know, we just made it up. I'm not going to elaborate on what I really means, because this is all you need to know for now. The integers, the rational numbers, the natural numbers, and the real numbers. This might take a bit of a long time because I'm just trying to explain it in a manner that you can understand, really, by giving you a lot of examples. Okay. First off, what even is a set? Or, like, what are sets? Sets, you see, they are a collection of distinct objects. Keep in mind also the word distinct. That'll be really important. Say for example, we have 1, 2, 3, 6, right? That's a set. But now you see, since we previously defined that sets are a collection of distinct objects, for example, I have 1, 1, 2, 2. You can see we have some repetitions here, so the objects aren't really distinct. That means this is not a set, but rather it's a multi-set. If I remember correctly, if I'm mistaken, please tell me in the comment section. Yeah, thank you. Now we're going to define the set builder notation. So the set builder notation is basically you get a variable that you want. Okay, if I want the set of even integers, I could start with 2n being 2 times n, and I could write down that n is an integer, either separated by a colon or just this line. That's the set builder notation that I want to talk about. So please keep this in mind because it might be really useful later for when you have to define some things. Now let's look at the empty set. When we define the empty set, it's this little thing right here. It's a set with no objects. That means you're always gonna have an empty set as a member of whatever your set is, because the empty set's got no objects. Now let's look at the set membership symbol. So this little weird E thing, it's supposed to imply that an object is a member of a set. And I can actually give examples right now. Wait. Implies that an object is a member of a set. For example, x equals a, b, c. We can say that a is inside of x like this. So d should not be inside of x. This right here is just the opposite of this thing. It says, oh, this is not in this. Right? I think that's pretty easy to understand. Right? Let's go to another definition. What do we say when two sets are equal? If I have a set that's 1, 2, 3, and a set that's 3, 1, 2, you would say, you probably say they're not equal, right? But, oh, joke's on you, the order doesn't matter. We can define A equals B. The order does not matter, just as long as they have the same elements inside of each other. Now, another definition, the cardinality of a set. The cardinality of a set we can write as this. Keep in mind that S is a placeholder variable. For example, A is equal to 1, 2, and 5, right? The cardinality says like how many objects you have in a set. I have 1, 2, and 5 right here. So the cardinality of A equals to 3 for this instance, right? Oh, why did I write curly brackets? And now, if I have B equals to this small b, and b is a natural number, like it's part of a set of natural numbers, This is saying that our set is 0, 1, 2, 3, 4, and like so on. So there's really no end when we define the cardinality of B. So the cardinality of B is just equal to infinity. Another thing I want you guys to understand is infinity is actually not a real number, because infinity is just a concept. This is a pretty basic knowledge, but maybe some people might not know, so I have to point that out. Let's go to the union and intersections now. Unions and intersections, sorry. Alright, the union we write as this symbol, and the intersection we write as this upside down U. What do we mean when we have the union and the intersections? Let me give you guys the examples. If I have S union with T, given that S and T are sets, it's going to be X where X is in S, or X is in T. Now keep in mind again that we have some other definitions, like this little V symbol being OR and this little upside down V being AND. My bad. So this that says OR, right? Which means if I have 1, 2, 3 unioned with like 1, 2, 3, 4, it's simply gonna be 1, 2, 3, and 4, because we're really just gathering the data from both sets, and the difference we make is that it just doesn't overlap. Now the intersection of S and T is, it's like the opposite of the intersection, where it's where X is part of S and X is part of T. Keep in mind, and X is part of T. If I have 1, 2, 3, 4 intersected with 1, 2, I just get 1, 2. And that's pretty interesting, right? So now we understand the union and intersections. This time around, we're going to define another weird set again. It's called the universal set. The universal set is the set of all possible objects. Now, when we write the universal set, we usually write it as this little squiggly U, because, I don't know, mathematicians probably thought it looked cool. Let's go over here real quick to a little corner note section, because there's something to tell you guys. There's going to be this little backwards E in set theory also. I don't think we're going to use it in this video, but it's really noteworthy. This means there exists. So I could say there exists an X that is an element of like a set Y, maybe. And a little inverted, no, just a little V symbol with a cross to it, and this means for all. So When we write it in set builder notation, I'll give you guys an example real quick. For example, I have this little big X as a set of X. For all X that is a member of the set of natural numbers. That's how I would do it, but sometimes maybe like there exists X that equals 2 for all X that is an element of natural numbers. And no shit, Sherlock, there is. Right? Let's go back to our section, and I'm going to give you guys example problems. Example problems 1. The first problem I want you guys to try is let A equal X, and X is a natural number. 0 is less than or equal to X, less than or equal to 6. And B equals to Y, natural numbers, and 3 less than or equal to Y, and Y is less than or equal to 5. So just find A union B. I'm gonna give you guys time to do this problem. I have to respond to a notification that I've gotten and just eat some bread. I was hungry before making this video. You could pause the video if you want, because no, actually you don't need to pause the video. This is actually pretty easy. Okay, got your solution. Let's see. First off, we see this right here. It's like a pretty big mess when you look at it, but really it's just A equals 0, 1, 2, 3, 4, 5, 6. And we see this thing here, B equals 3, 4, 5, because we define the inequalities. So the union of A and B would just equal to A, and so the answer is 0, 1, 2, 3, 4, 5, and 6. Wasn't that simple? Or just like too easy, maybe? Let's check out other problems now. So problem number 2, let A equal to 4, 27, 256, 3,125, and so on. So I want you guys to just express A in set builder notation. Okay. Pause the video, get your solution. This one's a bit tricky because you have to express it in set builder notation. Pause the video if you want. Oh man, this bread is so good. Alright, did you get your solution? Let's see if you're correct. What do we see? 4 is 2 to the power of 2, right? And 27 is 3 to the power of 3. 256 is 4 to the power of 4. And 3,125 is 5 to the power of 5. Now we just redefine everything. A is equal to x to the power of x. And x is a natural number. Whereas x is greater than or equal to 2. And boom, there's the answer. So I lied. It's still easy. It's not hard yet. Let's see. Okay, the recording's been running for 20 minutes. Let's quickly go over De Morgan's laws. Hold on, wait. Fuck. I forgot something. Wait, fuck. Okay. I think this is all the basic set theory, actually. You don't really need to know about De Morgan's laws yet. Okay, so I think that's the basic set theory. But I want to add one last thing and just get some more definitions down. Okay, the complement of a set is just the collection of objects in the universal set that are not in the set. So it's written as S with a C superscript, whereas SC equals to X, where X is in the universal set and X is not in S. Let's say you might as well think of it as I don't have an example, my bad. Okay. Last thing I want to tell you about, subsets. These things are really cool. So when I define with this little thing, this means B contains A in it, right? Now let's look over here. We could say B is this A as well. Now, keep in mind that if we have S as a subset of T and S is not equal to T, then S is a proper subset of T. Okay, that's the proper subsets definition. And fun fact, the empty set is a subset of every set. You always have the empty set. Always. Okay. I think maybe I should probably end it here for now as a part 1. There's actually much more things I need to cover for basic set theory. Okay, that's all for this video. I'll see you guys in the next part where we will actually use the for all symbol. The there exists symbol. Just throw that away. Forget about it. Alright, bye bye guys. Thank you for watching. No. Sin Q over cos Q for watching. Tan Q.